So thanks everybody for joining today. We have a follow-up presentation to a topic that we talked about, I think about a year ago, maybe a little bit more. It's an update on the NetBASILISK project from the University of Michigan. And today we have Jim Guhit, who's going to be going through the status of this effort and talking a little bit about some of the results that they've had during their implementation and operation phase. So Jim, I will turn it over to you.
Hi, can everyone hear me?
Yep, loud and clear.
Okay, hi. Good afternoon, everyone. My name is Jem, and I'm a graduate student from the University of Michigan. On behalf of the NetBASILISK collaboration, today I'll be presenting my work for the past year, which is benchmarking NetBASILISK, a network security project for science. All right, so today's talk is divided into three parts: our motivation and introduction of NetBASILISK, the framework program, and our ongoing and future work. In the first part, I will be going over the pros and cons of our current security methods, and then shift towards what NetBASILISK is and how it is currently deployed at University of Michigan. And then the second part focuses on the framework program that I developed, which tests the impact of NetBASILISK for science data coming into the University of Michigan. And this framework components consist of a benchmark, an environment monitoring application, and I will be showing how these components work together with the AGL22 framework and how the current output of the framework fits into my research goal. And the last part will be our ongoing work. I developed an independent environment service program, and also we have our ongoing work with the Perfsoner with the framework program that I also developed with Ed. So we're going to first move towards the motivation. Okay. Every day, any data, whether it's general, business, or science purpose type of data is connected to the internet, are susceptible to threats. And we want to enable high bandwidth network research and at the same time maintain privacy. However, achieving both of these goals at the same time is a challenge because achieving high bandwidth is often at odds with maintaining privacy and protecting data. So to address these issues, I will discuss the two tools currently used to block malicious threats, followed by how NetBASILISK aims to provide unrestricted access to networking for all applications. Okay, you see my laser pointer? Okay, so firewall is a physical network security device located between the internal network and the internet. And the diagram on the left shows a general structure of a firewall configured in a university setting. So the data coming from the internet first goes through the first level of firewall, then passes through the border router, followed by the internal network core routers. And then it gets rerouted to this their respective academic data centers. But you can see that it also passes a second level of firewall. So firewalls are placed all over the network so we could monitor incoming and outgoing network traffic, and it inspects data packets based on a set of rules. And most common rules include IP addresses, domain names, and ports. So I will give an example of how firewalls can affect science data. So let's say that we have a firewall and it's configured to block data coming from, let's say, for example, port 22. And we have scientific data that's coming in from port 22. So this means that all of these science data will get blocked as well. So even though firewalls are very useful for other use cases, it is not the ideal solution for scientific research because it slows down data import and export. And a solution that were made to firewalls would be the science DMZs. And it is a high performance science network developed by ESNet, which separates general purpose applications so that the goal is to each network could be optimized without interfering with one another. So the figures at the upper and bottom left corner is an example of a simple and big science data DMZ architectures. And even though the big data science DMZ looks more complicated, it has the same main components as the simple science DMZ, which is we have a wide area network, a border router, a science DMZ, and these are routers that are configured to pass science data specifically. And we have our data transfer nodes or DTNs, and we have the firewalls and the campus local area network. So I'm going to first discuss what would happen if science DMZs did not exist. So assume that our science DMZs here are not part of the network yet. So our regular path would be going from the wide area network, the border router, the firewalls, and the campus local area network. And this regular path is open to the uncertainty coming from the wide area network. And this is where all of our malicious threat could come from. And we also have the firewall performance issues as we discussed in the previous slides. So Science DMZs plan to improve this performance by separating the network into a high and low latency path. So the green path defined here on both figures is known as the high latency path or the long distance path. So this path is configured to specialize to pass science data. So these data do not pass the firewall. That's why we can ensure that it has high bandwidth performance. And the data, as you can see, is stored in this data storage nodes or DTN. So it stays there until a user from the campus local area network, for example, me, I want to access a specific data. So then if I want to go access a data, then the science data from the DTN goes through the low latency path now, which is our red path. So this is a short distance, and this is local within the university network. So even though our science data for this red path goes through the firewalls, low latency decreases the effects of the firewall. And so one of the downsides of the science DMZ is that it has more potential, the science data that passes through it is more potentially vulnerable to threats compared to our general purpose servers that go through a firewall. So this is the current network architecture of U of M. So I will discuss this from right to left. So on the right, we have our wide area network. And this part is showing the commercial internet. This is widely used by everyone. And some of the commercial services are connected to the RNE networks. In this case, we have Internet to Omnipop and Merit. And this connects the whole of U of M, University of Michigan, to the internet. And so we also have the network border security, which is the firewalls, and followed by the border routers right here and the internal network core routers. And these reroutes the data to the specific data centers. So the current architecture includes some of the characteristics of the Science DMZ. I think they're using some of the routers to pass specific scientific data, but we could see that the firewalls are still within the research path. So now that we have an idea of how firewalls affect movement of science data within institutions and how science DMZs separate the network so to improve performance, now we could talk about how NetBASILISK would expand, modify science DMZs. So NetBASILISK is currently in production. It's a network security solution that observes and monitors the network without interfering and distorting the data. So the main concept of NetBASILISK could be summarized in 3 main steps. So we copy, we analyze, and we connect or communicate. So first, it makes a copy of the data coming to and from the physical devices through an optical tap, and this is just one method. And then it analyzes data packets to determine possible threats. And then once a data is determined to have malicious threats, it communicates to the routers or firewalls so we could reconfigure and update the system. So here's an example of the Science DMZ for a big data site. So if we're going to deploy NetBASILISK, this would be implemented between the provider edge. So from the previous U of M architecture where the internet service providers, Internet to Omnipop and Merit were located in between those and the border routers, which is the gate to U of M Institute. So this the next slide talks about how we're deploying NetBASILISK at University of Michigan, and we're planning to integrate it within the existing U of M network border architecture, which was shown a few slides ago. And as I said in the previous slide, NetBASILISK has 3 main components: copy data, analyze data, and communicate with routers and firewalls. And there are several ways that we could implement this. So today I'll be showing you how we are implementing NetBASILISK at U of M based on the availability of hardware and software. So the first slide just shows the bare network. So we have the ISP providers, Internet to Omnipop and Merit, and this is the border router, so the gateway to University of Michigan. So we add courses, which are network devices that are deployed inline, mostly commonly known as bump in the wire. So it's very highly high-tech firewalls that doesn't interfere with the network performance. So these devices are also used for policy enforcements, and you can see how this would work out in a few slides. So the optical tap, it makes a copy of the live network traffic and it forwards it on for processing. So this taps, what it does is that it allows some of the light from the fiber to pass through and then the others reflecting it to another path. And then we have Mitten over here. So this functions as our repository containing internet protocol, IP addresses, domains, email addresses that are known to be malicious. So Mitten is a repository containing information of what is defined as a malicious threat. And you will see how this will communicate with the policy enforcement courses in a bit. So as I said earlier, optical taps makes copy of the data. So the copied data are fed into Arista switches, and Arista switches forward this data to Zeek. So Zeek is our software program that we use to analyze traffic data. So what it does is that it formats the data that it receives into well-structured log files for further in-depth analysis. So this is the complete prototype deployment. So just a recap, the first step is that optical taps make a copy of the data. It gets forwarded to Zeek through the Arista switch. And then Zeek parses and organizes the data into structured log files for in-depth analysis. It communicates with Mitten. As I mentioned earlier, Mitten contains information about the malware patterns. So once the data has been identified to have malicious content, Zeek relays this information to Mitten, and Mitten communicates with the courses, and courses will enforce this policy to reconfigure the firewalls and router. And at the same time, Zeek also uploads all of the log files to Humio database. So now that we have an idea of how NetBASILISK is currently being deployed here at University of Michigan, its effectiveness will be quantified using these three main use cases because they represent data-intensive science. So we have three. So physics and cryo-EM, they are examples of large-scale movement in and out of the university. While EECS, which is our computer science department, this is an example of a research group that observes and studies the network. And so this is where I come in. I'm working on the physics use case, and my research goal would be to evaluate the impact of NetBASILISK on science data coming into, so one way, going inside University of Michigan. So to evaluate NetBASILISK's performance, I developed a framework program that is made up of two components, a benchmark and the environment monitoring application. The benchmark application, it focuses on simulating data movement from an external source coming into the University of Michigan network. And the main deliverable of this application would be our bandwidth or transfer rate. And this is how we base transfer performance. And as for the environment monitoring application, it focuses on monitoring other factors that could impact data movement that is independent of NetBASILISK. The main deliverable of this application would be network metrics from the source, destination, and network in between the source and destination. So that the purpose of this, so that we could rule out any external factors that could affect data movement that is other than NetBASILISK. So now we move on to the next part of the talk, and the section introduces the framework components, which is the benchmark and the environment monitoring application. So for the benchmark, we're going to discuss what type of data we're moving and how we're moving it. And for the environment application, I'm going to discuss which is our source, our destination, and the path in between, and also what type of network metrics we are grabbing for each path. So starting with the diagram on the left, the benchmark components facilitate the data movement from Brookhaven National Laboratory, or BNL, to AGLT2 server at the University of Michigan. And a transfer client tool is used to transfer files from the source to the destination server. And then as for the environment component on the right side of the figure, we have to grab network metrics from the interfaces in the source, destination, and the network in between. And I will be discussing this in more detail in the next slides. So now we focus first on the benchmark application. So the data that we're using is a repository of Atlas datasets that's located in BNL. And as for the transfer tool, this is a software framework tool that we could use to access Atlas data repositories and transfer files from BNL to University of Michigan. So as you can see in this table, there are many known storage clients. So in order to decide, we created the following requirements that the storage client has to satisfy. So we originally thought of having only one storage client test. However, the first round of storage client tests, which is just running multiple data transfers 10 times, you could see that 2 storage clients satisfied the criteria. So now we have to go to another round of test. So the second round of storage client test is virtually the same as the first one, but this time we focused on which storage client would provide the most stable file transfer performance over a period of time. So in addition, we looked at some metrics like the average and the standard deviation, and we compared it for both storage clients. So as you can see in figure 1, it shows that from the second round, we could see that Globus has more variability, and XRD is more stable in terms of its transfer performance. So we determined that XRD is the better official transfer tool to use in our case compared to Globus. So we use XRD as our official transfer tool for the benchmark application. Now, moving on to the environment monitoring application, the previous section, we focused on the benchmark test so we can evaluate transfer performance. And so there are also other factors, as I mentioned earlier, that are independent of NetBASILISK that might affect data transfer performance. So there are three possible sources. So one would be the network at the source. So we define this as our BNL end system, network at the destination, which is our AGLT2 end system, and the network in between, which we define as our wide area network or middle system. And I divided this WAN into two subparts, which you'll understand a bit later. So for the BNL end system, there's a network monitoring that exists for BNL. However, we didn't have any easy access to these systems. So right now we assume that the internal networking at BNL, it's well provisioned. So we assume that it's not going to limit our benchmark transfers. And as for the AGLT2 end system, we have a monitoring interface available. And so the software that we use to monitor the AGLT2 cluster system is CheckMK. So all of the transferred files that goes into the AGLT2 cluster, they are stored in one of the UMFS servers. It's called UMFS servers. So you can see the figure on the bottom right. It contains a variety of network metadata that we could get. So we just chose a couple of metrics of interest that could give us an idea of the overall status of the network. So a couple of these would be CPU load, utilization, memory, and disk I/O. As for the middle system, I divided it into two parts. So BNL going to the ESNet location in Chicago, and then the ESNet location in Chicago going to AGLT2. Currently, ESNet uses internal engineering. So right now we don't have a way to identify the path and interfaces, but we assume that since ESNet is using its own internal traffic engineering, we are going to assume that it's not going to affect also our the transfer performance. And then for the next part, which is ESNet Chicago to AGLT2, we have some more accessible monitoring tools. So the figure on the right shows the ESNet presence in Chicago at the top of the figure, and it goes down all the way to Shinano, which is our AGLT2 border router. So I divided this diagram as well into two parts because we have the Chicago paths, which is 600 west and 710 north. This is controlled by the Grafana interface. And this figure on the bottom left just shows the Grafana interface and the metrics that we're grabbing, which is the input and output bandwidth. And the second part of the diagram is our Arbin SEB router. So this is the internal router for the University of Michigan. And this is monitored by the CA Performance Center. And this is also the following the metrics that we're grabbing. And Shinano at the bottom, as discussed 2 slides ago, this is AGLT2, and this is monitored by the CheckMK. And this figure just shows the CA Performance Center, and this is one of the ports, ET430, and you can see that I'm grabbing utilization here, for example. So now that I've given you information about the benchmark and the environment monitoring application, I will discuss how this whole framework, how I built the whole framework from start to finish. So this is what I call the AGLT2 framework program, and this is the framework from start to finish. So the upper diagram focuses on the logic flow of the framework, and the bottom part shows the parallel scripts that are involved. So the script begins by running the benchmark script. This facilitates the data movement. So this is our benchmark application, followed by the environment script, which grabs network metrics from the source, middle systems, and the destination. So once we have the output from both benchmark and environment script, I created this pre-processing module. So what it does is that it parses organizes the output from both monitoring, benchmark and environment outputs, and it stores it into a huge data structure and it sends it to the Humio database. So in the previous slide, I talked about the whole structure of the framework and that I have this output that is being sent to the Humio database. So in this section, I'm going to talk about how this output looks like and how we plan to interpret this metrics. Okay. So the figure on the left shows the overall framework structure. So we could see that the BNL N system and the BNL to ESNet Chicago system are here in this framework, but since we are not yet grabbing metrics from this point, these are just crossed out, but I just put it all for completion. And so we are currently actively working with BNL and ESNet so we could eventually gain access to these points. So the results of the framework program, these are used to define a threshold to what we define as a busy, medium, and free network. So once these definitions are defined, we can use it in the framework score scheme that we have developed. You would see in the next few slides. So this framework score scheme, we will use this to interpret future results of our future framework runs. So the first part of the data structure is our benchmark results, and this is on the right side. If you look at side by side, this is under summary. So this just shows metadata about the benchmark results. So one of the key metrics that we're interested at is the bandwidth, because this shows our transfer performance, how fast the data is being transferred from BNL to AGLT2. And for the environment monitoring application, so we skip parts A and B because we don't have information about those yet. So in part C, we have the middle system, ESNet Chicago to AGLT2. So on the left side, you could see the Chicago paths, 600 West and 710 North. And then we have the ARBIN-SAB, which is the internal router. And then the last part is we have the AGLT2N system. And this shows the metrics, which so CPU load, utilization, disk IO, and memory for the different UMFS servers. So we have a couple of UMFS servers. So the data that we transfer from BNL, it could go into one of these UMFS servers. So that's why we had to grab metrics from all of them. So as I mentioned earlier, we use the early results of the framework ones to define what is okay, warning, and critical thresholds. And after these are defined and fixed, we're going to use these definitions to interpret our future runs of the framework program. So I will give you an example of how we interpret this framework score using these two cases that we have. And this would show how we could identify how NetBASILISK will impact incoming data transfers. So if we focus on case one, so case one shows that the critical transfer speed is due to NetBASILISK. So if we check this table, all of our environment networks are okay. So they're free, congestion free. But however, we still are getting a critical transfer speed. So most likely, if our environment our testing environment is okay and we're still having a bad transfer speed, then this indicates most likely that the problem is caused by NetBASILISK. In case two, we still have a critical transfer speed, but we can see that our testing environment is not so free. It's a bit congested. So case two is focusing on the cause of this critical transfer speed is due to the testing environment. So we can see that probably it might be a source destination node problem. So this just ties up to my research goal. So we created this framework score scheme so that we can evaluate whether NetBASILISK or other independent sources are impacting the data movement into our network. Okay, so moving on, the framework program is automated and we are sending data regularly to Humio. And at the moment, we are also working on two projects that we have here that is also important to the project. So I'm going to start with the independent environment service. So as I said earlier, we wanted to define what is okay, warning, and critical thresholds for our framework score. So the benchmark script is only ran a couple of times because if we ran the whole framework program too often, it will saturate the network. So we thought that it would be good to have an independent service, independent environment service, so we could grab data in a more so we could grab environment data in a more frequent rate. So we could use those to define the baselines for the environment metrics. So what this figure shows is that this is the whole framework script earlier. So what I did is that I scripted the environment script and the pre-processing script by itself to create the independent environment service. So I don't have to transfer data all the time. I would grab environment metrics more frequently. So how it would work is that I'm using cron, and I automated this so I could grab metrics from the network every 5 minutes. And so I could just run this for a whole month and see the variability of the environment metrics over a long period of time. So the output is also organized in a JSON file. And so we plan to send this to a CheckMK host so that we could create a business intelligence. So the figure, this is an example of a business intelligence. So what we plan to do is that, for example, this could be the environment service and then the 3 main paths that we have in the network, and it could summarize all of the metrics that we gathered, and we can easily see if it's working okay, warning, and critical. So once this independent environment service is fully working, the future runs of the AGL2 framework script, it will grab environment metrics from this CheckMK business intelligence host. And so the last part of our ongoing work would be including Perfsoner to the framework program that we developed. Okay, so just an overview, what is Perfsoner? So Perfsoner, it is a project that is dedicated to generating network metrics, and it implements the different tests. So the different tests that it could run would be throughput, RTT, latency, and trace. And it runs this test using open source tools. So for throughput, for example, iPerf, ping for RTT, and so on. And so what happens is that after these tests are run, the results are sent into an archive. So for example, this is the results are sent through an HTTP protocol through Logstash, and Logstash sends this to Humio Archiver. And then once the data is in the Humio Archiver, the user could do different types of visualizations depending on their goal. So in the next slide, I will be giving an example of how this was done for the BNL to University of Michigan path. So this is an example if U of M wants to send a p-scheduler request to BNL. So once that happens, BNL would run the test. So for example, throughput, latency, and then it sends the raw data to University of Michigan. So University of Michigan uses the HTTP protocol and sends the raw data to Logstash. And what Logstash will do is that it would parse, pre-process, and format the results and send it to Humio. And so on the last part here, if you have a user, for example, me, I can view the formatted results and I could do visualization or do some sort of analysis in Humio. So the main purpose of why we thought of including Perfsoner on top of the framework program is that since Perfsoner makes an end-to-end network measurement, it could cross-check the middle system of the environment application, because we're also grabbing environment metrics in our middle system. So Perfsoner could be a good cross-check for this because it does an end-to-end network measurement. Okay. So this slide discusses what it would look like if we add Perfsoner to the framework components into our framework score. So for the first case, this is still critical transfer speed due to NetBASILISK. So we could see that the environment metrics are okay. And if the Perfsoner network is also okay, but we still have poor transfer results, this could indicate that most likely the problem is caused by NetBASILISK. And as for case 2, we could see that this critical transfer speed could be probably due to the network, or specifically the data transfer node. Because if we look at this table, our testing environment is a bit critical because you can see that the source is a bit critical. The network is a bit, you may say, in the middle, and the destination is okay. But Perfsoner is okay, so which means that the network is doing fine. And then our speed is still bad. So which means that the problem is lying on the environment path and specifically on the source storage node. And on case 3, this is the most ambiguous part, I would say, because the critical transfer speed could be caused by either NetBASILISK or the network. So we could see here that our testing environment gives us a warning. So our source is a bit bad, but the network is doing okay and the destination is doing okay. But Perfsoner is doing bad. And as I said earlier, we're using Perfsoner to cross-check our network in between or our middle systems. So if our network is doing okay and Perfsoner is telling me that it's bad, the end-to-end measurement that it saw is not doing well, then the poor transfer speed could likely indicate that we have to look at both the network and NetBASILISK. So that sums up our ongoing work. And now I'm just going to conclude what I've discussed in the past few slides. So currently, as for the framework program, we're currently working with BNL and ESNet with our authentication issue so that we could start gathering the additional missing network metrics. And so the accessible parts of the framework script is already scripted, it's automated, and the output is sent to the Humio database automatically. And so for the independent environment service, this is also scripted, automated, but currently the output is sent to a local storage. So right now I'm configuring how to send this output to the CheckMK host so we could build a business intelligent. And so the main focus of the next phase would be to analyze our benchmark and environment metadata so that we could define the thresholds for what we define as the okay, warning, and critical, so that for the framework score, so that we could use that to interpret our future framework runs. And I also want to thank Drew Dixon for our data security analyst for having useful discussions about U of M network architecture. And then for more information, we publish all of our codes for the AGLT2 framework and the environment monitoring in this GitHub page. And also this is our current preprint for this preprint paper for this project. So far, that's all I have.
All right, thank you so much for going through that, Jem. We did have one question that came in during the talk here. Actually, it's more of a comment from Andy. It's likely safe to assume that the far end systems networking is good in the case that you mentioned. However, in general, be careful about that assumption, because Andy has run into cases where they assume that the one end was okay, and they were able to sort of determine that there were problems, but they only figured that out by doing hop-to-hop testing. So that's one thing to consider.
All right. Okay. So I guess a question to Andy is like, how do we add this to factor this in so that we would be more aware with this? Because I don't think I have added this when I was developing the framework.
Sure. So actually, let me see, Andy. I'm just going to unmute you because it's probably going to be easier to talk than to try to type all that out. So you can unmute yourself if you'd like, Andy.
I wasn't planning on talking, so hopefully you can hear with this mic.
Yep.
Just kind of more a case of, and when you started the talk, you were saying that, you assumed that the networking at the far end was good when you were doing your like baselining. And I guess I would try to get a for lack of a better idea, maybe a Perfsoner node, in that same VLAN subnet, as close to those two end servers as you can get, and do your Perfsoner testing also during your benchmarking stage to make sure that Perfsoner from end to end, not just from border of the network or border of the campus to border of the campus, but end to end host, that Perfsoner comes back clean when you're doing that initial benchmarking or baselining of the existing environment. Does that make sense?
Yes, yes, I think, yes, it does.
Because like in this case, Perfsoner was showing clean even when we went from the RENS network, our network, up to a Perfsoner node at the border of the R1 institution. But when we got them to throw up a Perfsoner node further into their network next to the destination, then we actually saw the problem show up in those Perfsoner tests also.
All right.
All right, thank you, Andy, for giving us that information. So I had a couple of questions that I jotted down as well, and I'll invite anybody else that has any that they'd like to point out, please type them into the chat room. So you're using sort of telemetry data from the tests that you guys are doing, and you're looking at Perfsoner data. Are there any future plans to instrument other data transfer tools or network tools to sort of use their live experiences as well to feed into this system, or are you just going to be relying sort of on the dedicated measurement tools to give information?
Can you repeat the last part? So are you asking if I'm going to rely on the dedicated tools? So you mean by dedicated tools would be Perfsoner, correct?
Yeah.
Yeah.
So right now you're using Perfsoner data, but would there be any work to try to instrument other data movement tools, like in the LHC use case, it would probably be Rusio or something like that, to sort of use information from that tool to understand if there's any problems?
I see. So because right now I'm just using extra D, so, and then using Perfsoner as well. So I don't think we have any specific plans yet to include other types of protocols, because right now what has happened is that if I go through this, just or I could just go back to the framework. 1 second. So if I go back to the framework, this framework is fully built and we've been sending data automatically to Humio now. But I said here earlier that we have to use the early runs to define OK, warning, and critical, and use that to for this framework score to interpret future runs. So I think since the next part of our phase is analyzing the metrics that we get to define these. So and we still haven't done that yet. We're still trying to define these values. We're still trying to stick to extra D for now and Perfsoner. And so I guess what I'm trying to say is probably later in the future, once we have this framework score fully defined, and we're actually using it actively to interpret future runs, and we fully understand how extra D works and Perfsoner altogether, then maybe we could start considering other protocols like Rusio, as you said.
Okay. All right. Well, thank you for answering that. I don't see any other questions that are coming in quite yet. So I'll put out a last call. If anybody else has anything that they'd like to ask or point out, please do. Thank you again for giving this presentation, Jem. If you can send me a copy of it, I'll make sure that it gets posted.
Yes, definitely.
Okay. All right. Looks like we don't have any other questions. So thank you again for going through that, and we'll make sure that we get all that stuff posted. And for people who are still listening, the talk next week is going to be from Julio Negron and George Robb, and they're going to be talking about the Arecibo Observatory and some of the data movement and the computing activities that are going on there recently after the collapse that happened in November of last year. So hopefully everybody can join that. Otherwise, have a good weekend, and we'll talk to everybody soon. Thank you so much.
Thank you.